So let's look at the algorithm that we use in order to generate the Mandelbrot set. So it's relatively straightforward. We're going to start off with a number z0, and this is the number 0. Now it's a complex number, so it's 0 plus 0i. Then we're going to go through this iteration. We're going to have z to the n plus 1 is zn squared plus c, where c is a complex number. So best seen by example, and we'll work through the example here, and then we will go on and look at it in the graphical calculator Desmos. So in this example we choose a number c, so the first one we've chosen here is 0.3 plus 0.2i. Now if you're not familiar with complex numbers, we can think about them quite simply as the set of real numbers which is along the x-axis, and the set of imaginary numbers, that is the number with the I here, along the y-axis. So if we were to plot this point off, we would still just plot it the same as we would whenever we plotted a normal point where both axes are real. So we would have this point here would be 0.3 along the x-axis, and this point here would be 0.2 along the y-axis. But remember now, the y-axis is actually an imaginary axis. So instead of the number line actually being a number line, what we have is a number plane. That is a plane of numbers. So we're going to start off with this z0 is 0 plus 0i, and then we're going to generate z1. So z1 is going to be the next one within this iterative loop. So it's going to equal z0 squared plus c. So we take the original value here, which is our 0 plus 0i, and then we add on the value of c, and this is the value of c here. So this here is our very next point. And then for the next one, we're going to have z1 squared plus the value of c. So we've already worked out what the value for our z1 is. z1 is this here. So we're going to take this z1 and we're going to square it. And then we're going to add on the number c, which is our original number here. So we add this number on. So we have to square these and then add these on. Now I've written out the entire process here for us going through that. I'm not going to talk about how to multiply together complex numbers. You can have a look online, it's relatively straightforward, and you've got all the details here of how it's actually done. So whenever we go through this process, we're going to end up with the next point here, 0.35 plus 0.32. Now we can continue on in this vein, and we can get as value for z3, which is z2 squared plus c, and that's this value here squared plus the c. And this gives us this output here. And then we take this output here and we square it and we add on the value of c. And we get this output here. And we continue doing this. So let's have a look at this in the graphical calculator. So we're going to start off with our first value, which is z0, which is just the origin. So that's 0 plus 0i. And then we can pick our value for our c. So this is the value for our c here, and you can see that we've chosen the value 0.3 plus 0.2i, and we can join these points together. Now this value here for our c could be any value, but for this particular example we're going to choose this value here. Now we're going to generate the value for our z2, and this is the value for our z2, and we can connect the lines together, and you can see it's the same as what we generated or what we've seen in the previous page. And then we can, whenever we change the value of our c, you can see that the value of our next number along is going to change as well. So you can see these changing. Now we'll put this back to the value of our 0.3 3 and the 0.2, and we'll put the rest of the numbers in. So the next one along is going to be our Z3, and we can connect the line. It's going to be our Z2, we'll connect our line, so Z3, and we can connect the line. And then the next one along is going to be a value of our Z4, and again we can connect the line for our Z4. And finally we've got our Z5. Okay, now we could keep connecting these lines, so we could get Z5, Z6, Z7, 8, and so on and so forth. In fact, I'll just flick through these. And you can see in this instance, whenever we choose this value 0.3 plus 0.2i, we're actually going to get the final value converging. So it's going to converge to this final point here. Now that's not always the case, because if we were to choose a different value here for our c, you can see that this could potentially just spiral off and spiral out to infinity. So it's only a subset of numbers that will allow this, if we like, to converge to a particular point. Now here is the last part of our Mandelbrot set algorithm, and this is a test. So we're looking to find the absolute value of Zn squared. So what does this really mean? So it boils down to the xn squared plus yn squared. So this in effect measures out the distance between the origin and the final complex number that we generate. So in the instance I showed you just a moment ago, we had 15 different iterations, so we ended up with like 15 different points. So if the very last point is within 4 of our origin, then we decide to keep that point, and that point is part of our Mandelbrot set, and it will be shown as a pixel in the final output. So let's have a quick look at that. So you'll see that we have our original point here, which is 0.3 plus I 0.2. And these are all of the rest of the points that we generate after our iterations. So you can see here that it's travelling around in this little decreasing spiral till it gets to the final point here. Now, if the distance between the origin and this final point here is, in our instance, we've chosen a value less than or equal to 4. Now you could choose different values and you're going to get slightly different results. But in our instance, we've chosen the value of 4. So if this distance is less than or equal to 4, then we say at this point here, we can put our little cross, and that becomes part of our Mandelbrot set. Now if we were to change this to a different point, so let's say our point moved over here, and the distance here of our blue line was greater than 4. So you can see here the blue line is actually heading off to infinity, so it's a lot greater than 4. So it means at this particular point, the example we've got here is 0.423, 0.1316. We won't have a dot or a cross. It won't be part of our Mandelbrot set. So you have access to this simulation, and in order to use it, you just have to grab the little brown or beige dot and you can drag it round about. So this dot here represents the value of our C. and you're able to see exactly what points are going to be within our Mandelbrot set. So let's go ahead and we will look at the final lot of points within the graphical calculator. Now I have gone ahead and generated all of the points that are within our Mandelbrot set. In the example that we have generated here, there's going to be 15 iterations, and we've chosen it such that the final value has to be less than or equal to a value of 4. Now, this isn't exactly what we're going to get whenever we generate this within our CPU, but it's going to be extremely close. So we can now go ahead and we'll have a look at the program, and then we'll run it and we'll see how close it is to what we expect to get. Now, one thing we should note before we continue is how we actually generate our little algorithm at the bottom here. So we're going to start off with the algorithm for our Mandelbrot set, which is z to the n plus 1 is equal to zn squared plus c. Now c is any complex number, so if we let c equal xc plus iyc, and then we know that zn is going to be a complex number, and we can call that x plus iy. So we need to generate the x new and the y new from this. Now we know how to do this because it's going to be z to the n plus 1 is equal to z to the n squared. Well, z to the n is going to be x plus iy squared plus the c, and this is the c here. So all we're really doing is going from this point here down to the line at the bottom, and I've actually gone through it in minute detail. So if we were to square this, then we're going to have this times this plus this. Now in order to multiply these out, we're going to have the x times the x times the iy, and then we're going to have the, again, x times the iy here, and then we're going to have the I squared and y squared. So when we get to the next line, we're going to have x squared, and we're going to have the ixy plus ixy plus I squared y squared, and at the very end we're going to have xc plus iyc. So that's going to give us the 2ixy, and it's going to again give us the I squared y squared and this value here. Now the value of our I squared is equal to minus 1, so this whole thing can get replaced by the minus y squared, so this I squared becomes minus 1. And then we're going to be left with our x squared minus the y squared plus the 2xyi plus the xc plus the yci. So we can see here we've got the real parts here and the imaginary parts. So if we split them up, we're going to have the real parts going to be given by x squared minus y squared plus xc, and the imaginary part is going to be 2xy plus yc. So that means that our final little part of the algorithm we're looking for is x new is going to be x squared minus y squared plus xc, and the y new is 2xy plus yc. But it's nothing other than just simply going through the algorithm here with a couple of complex numbers, and then after we've worked through, we separate everything out into the real part and the imaginary part, and these are what we're going to use within our algorithm. Now this is the low definition Mandelbrot set assembly language code, which was generated by Timothy Morgan. And you can see here that we're going to be scaling the coordinate pixels so that they're going to be in the range minus 2.5 to 0.5 for the x coordinate and the minus 1.5 to 1.5 for the y coordinate. We're going to have the maximum iterations of 15, and then we've got the little algorithm here. So we're going to be looking at the x squared plus y squared is less than or equal to 4. So this was our little pink line which we've seen. We're going to have the x coordinate, which is generated by x squared minus y squared plus c, which we've just seen a second ago, and then the y coordinate is 2xy plus yc. So this will give us the real value and this will give us the imaginary value. And then we're going to work through the iterations for this until the value we get out is, if the value for the final iteration is less than or equal to 4, it's part of the Mandelbrot set and it gets plotted. If it isn't, it's not part of the set and doesn't get plotted. So this is the basic algorithm here. If we head down into the code, I'm not going to go through every single detail of the code line per line, but we're going to start off with the graphics library here, in which we use the plot command, which is at this location. We've got a colour defined here as pink. We've got our constants here, which are the maximum iterations, which we mentioned as 15. We've got the maximum and minimum points here in terms of an integer value and also in terms of a floating point value. These values here have been generated because what we're doing is, if we were to generate the Mandelbrot set, then it would be rather small on the screen. So that is, we would only have it converging for a small number of values. So what we can do is, we defined the number of values as running from minus 2.5 to 0.5 in the x direction, and also plus and minus 1.5 in the y direction. So in effect, we've got a total of a distance of 3 in both the x and the y directions. But if we were to try to plot this out, the plot is obviously not going to work because we're only going to get a few pixels between the minus 3 and the plus minus 2.5 and the 0.5. So it would be tiny, we wouldn't be able to see anything. So we're going to have to expand that up. We have to go and stretch that or enlarge it. So what we have to do is take the distance 0 to 3 in the x direction and the 0 to 3 in the y direction, and they have to be plotted on the full screen size, which is going to be the minus 128 to plus 127 and then the minus 127 to plus 128 for the x and the y directions. So we've got these values here that we use for the scaling. Now the main part of the program is here, and we're going to first of all go through the minimum values in the register for both the integer and the floating point. And then we're going to jump to the main part of the code here, which is determining whether the point is going to be in the Mandelbrot set. So we'll go to this mand_pix. So we head down to mand_pix here. So this is the main part of the code. So we're going to do the tidying up first of all. So we'll push all of the values before we pop them all back off again. So we're going to go through the scaling in the y direction, and this is the scaling from minus 1.5 to 1.5 up to minus 127 to the 128. And this is the little algorithm that we use for the scaling. We then move on to the scaling on the x-axis, and again we scale from these points up to these points, and here's the little algorithm for the scaling. So once they've been scaled up, we can go through the iterations. So we're going to have to generate the algorithm for our Mandelbrot set. And the algorithm which we looked at earlier is the values for our next x value, which is x squared minus y squared plus xc, and then the value for the next y, which is 2xy plus the yc. And this is going to be generated and then passed back into the algorithm as the next value. And we're going to be running through this a total of 15 times. And you can see here the comparison with the counter, which is in the index register, and the maximum iterations, which is in register R5. So once we've exhausted that count, we can jump to return 1. So the ret 1 is down at the bottom of this little iteration loop. So it's going to jump to the mand underscore done. So we head to mand underscore done, which is this point here, and it's going to restore all of the register values and return back to the original call to this little subroutine. So this is the subroutine, and we were called to this subroutine from up within here, this point here. So it's going to return back to this point here. If the value returned as a 0, then it's not within the Mandelbrot set and we don't plot it. Now if it is, then we continue down to the next couple of lines and we go through and we plot it out. We then pop these values back off. We then go through and we add the values onto our xc and our xp to get the next points. And then we're in a position to jump through the same loop again and again until eventually we work our way through the entire -128 to +127 in the x, and also the -127 to 128 in the y direction. So that was a bit of a rough and ready explanation of a really nice piece of code. So let's go ahead and we'll look at the actual output of this code and compare it to what we expected to see within the graphical calculator Desmos. On the left we have the output from the CPU. On the right we have the output from the graphical calculator, and you can see the similarities. Now it's not a particularly scientific comparison, but we could go through and just look at each of the individual pixels, from the picture on the right to the picture on the left. So as I said in the last video, it's a good time to take stock of how far we have come over the last 4 courses. And there are lots of other functions which we could generate within our CPU. Now one that springs to mind is the fast Fourier transform algorithm, and that's something I may work on out with this course and then add it in at some point in the future. But there are lots and lots of other fantastic mathematical functions which we can now go and simulate within our very own CPU. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.